Let us now discuss statics of rigid bodies. So far in 3 lectures, we were discussing the statics of particles, the forces that are acting on a particle. Now we will move on to the rigid bodies. When we are discussing about rigid bodies, we have to use the equilibrium equations. This is what we really want to understand in detail. But before we get into this equilibrium of rigid bodies, we need to understand certain concepts. Particularly, 3 major concepts we need to understand. The first concept is moment of a force about a point. Moment of a force about a point. Then moment of a force about an axis. Then we need to understand the concept of couple. In this course, in this lecture, we are going to first see what is this concept. We need to understand this concept first, then we will understand this, then couple, then we will move on to the equilibrium of rigid bodies. Before getting into moment of a force about a point, let us first understand one principle called principle of transmissibility. What is this principle of transmissibility? Say for example, you have a rigid body. A force is acting in this direction, a force of magnitude F acting in this direction. Say this is the line of action. This is the line of action of the force. According to principle of transmissibility, the condition of the equilibrium or motion of a rigid body will not change when the same amount of force, a force of same magnitude, equal magnitude and same direction, which is acting in the same line of action. Now this force and this force are equal. So if I take this as F dash, F vector equal to F dash vector. So the principle of transmissibility is this force acting here or here in the same line of action, as long as the force is in the same line of action. So this force is replaced with this force and the force is acting in the same line of action. Okay, then the condition of equilibrium or the condition of motion will not change. That means the effect is unchanged as long as the force is in the same, acting in the same line of action. You understood this? Say for example, you take a truck. Okay, this is the line of action. You push the truck with some 1000 Newton. Okay, the same line of action, if you pull the same magnitude, replacing now and applying the same force in the same line of action, the condition of motion will not be changed. What this force is causing, the same thing will be caused by this force on the body. This is principle of transmissibility, and this principle is greatly used when we discuss the concept of moment. Let us first understand the moment. Before really getting into the stuff, we'll see a cross product of vector. Okay, some vector we'll see now, which you would have already studied. Okay, say for example you take a plane. Let us assume this is a plane where two forces are acting. Let us take this as P and this as Q vector, and the angle is theta. See, these two vectors are in a same plane. Then the vector perpendicular to this plane, let us take that vector as V vector, is P vector cross Q vector. Okay, so now the vector which is perpendicular to P and Q, which are in the same plane, is P vector cross Q vector. Okay, now if we write in terms of rectangular coordinates, Px I vector plus Py j vector plus Pz k vector cross P Qx I vector plus Qy j vector plus Qz k vector. If we multiply, finally we get this V vector can be represented in terms of matrix determinant. This is Px, this is Py, this is Pz, and Qx, Qy, and Qz. We'll have this. Now we are going to understand the moment. Say, assume this is the rigid body. This is the rigid body, and take this corner as the point, any point. Okay, and I am applying some force like this. What is the tendency of this force? Generally, the tendency of the force is translating. If it is fixed, then the tendency will be translating as well as rotating. Okay, the force will try to pull it as well as try to rotate it. Okay, if the position vector and this force vector are in a same plane, okay, assume you see this and the plane, same plane, and then the moment is okay vertical to those two vectors, the position vector and the force vector lying on a same plane, and it will be perpendicular to the plane about that point. Okay, so now the direction of the moment is this. Okay, so you can use the right hand. This force is tending to rotate the body anti-clockwise, and the thumb shows the direction of the moment. Okay, let us take a rigid body. So this is the point, some point. You take this point O, and some force vector okay, and the plane, and this is the position vector or vector, okay. Let us take this as the plane, and then this is the plane on which R vector and F vector are lying, and then this is moment vector. According to this, okay, this is R vector cross F vector. So moment about a point is a vector, and it is represented vectorially or cross F vector, right? Now what is the magnitude of it? Okay, you know the angle between R and F, if we just extend, this is theta, okay, and draw the same line of action. Here comes the principle of transmissibility. The same line of action, if the force is replaced anywhere in the line of action, the effect will not be changed. So if we find the perpendicular distance, this is 90 minus theta, and R cos 90 minus theta is sin theta. So R sin theta, we will get R sin theta as perpendicular distance. So what is this? R F sin theta. Here the magnitude, what you have already learned, the magnitude is P Q sin theta. This is what you would have learned already, okay. So the moment magnitude is R F sin theta. So F R sin theta, R sin theta if I am taking as D, then this R sin theta is D, it is nothing but F into D. So moment, magnitude of the moment is force into perpendicular distance. This is the force, and this is what is the definition of moment? Moment is force into perpendicular distance. That is the magnitude of moment. Now you see this force, when you are seeing this, we are using this, so it is going to rotate the body clockwise anti-clockwise direction. So the anti-clockwise direction is taken as positive. Okay. Now the clockwise, if the force is acting like this and about this point it is rotating clockwise, then this will change like this. Okay, it is rotating clockwise and the direction is this, it is opposite to the anti-clockwise direction. So this becomes negative. It's a free choice. Conventionally we can take anti-clockwise as positive, clockwise as negative. So it has a magnitude and direction. So moment is a vector which is having a magnitude and direction. Then what does this moment signify? It is a measure of the tendency of the force on the body. So the tendency of the body is rotating. So understand one more principle called Varignon. Say in a coordinate system x, y, z, assume there is a point, a concurrent point where some forces are acting, say F1, say F2 and F3. These three forces may be acting in space. It is not a planar force, in space. Now from reference, this is going to be the position vector. These concurrent forces or the forces that are acting at this point will have a resultant. We know that. So what does this Varignon principle says? Okay, the moment of the resultant about O or cross, say this is the resultant of F1, F2, F3 vectors, right? So the moment of the resultant about O is equal to sum of the moments of each force about O. R vector cross F1 vector plus R vector cross F2 vector plus R vector cross F3 vector, and so on. We have more forces. Okay, I repeat again. The moment of the resultant force about O is equal to moment of the summation of the moments of each individual force about O. Okay, this is Varignon principle. So then, if you have only one force, say you have only one force, it will have components Fx, Fy, Fz. Okay, then the Varignon can be applied for that components as well, rectangular components as well. What is it? So it is the resultant of Fx, Fy and Fz. So the resultant about O about a particular point is equal to summation of the components, moments of the component forces about the same point. Okay, so it can be applied for the rectangular components as well. We will be extensively using this principle of transmissibility and Varignon principle when we are dealing with these moments, couples and so on. Okay, now let us see the rectangular components of moment. Say you have X, Y and Z, one force, and then this is the position vector, and say this is the force. So then it will have Fx I vector, Fy j vector, and Fz k vector, right? So now R vector moment about O vector is R vector cross F vector. Okay, now we can write cross Fx I vector plus Fy j vector plus Fz k vector. So now I have elaborated with the rectangular components. Okay, now if you are multiplying, then you will get I vector, j vector, k vector, x, y, z, fx, fy, fz. Determinant of a force in 3D or in space. Okay, the moment can be obtained, or the moment vector can be obtained using this determinant. So the x position, so what is x? This is the x distance, this is the y distance, and how much z distance with respect to O to this point we need to know. So these are the coordinate points. Now say for example, okay, and erase it a little, okay. The same force y fx I vector f z k vector. Okay, now if we have to take moment about another point, say this is A and you want to take moment about another point, okay, then what is the x distance? This is x distance and this is y distance, and similarly the z distance between A and B, okay. So this is position vector RB, this is position vector RA, and this vector is R, okay, A with respect to B vector. So this plus this gives this. So R B vector plus R A vector, what does it mean? A vector with respect to B, okay, equal to R A vector. So R A B vector equal to R A vector minus R B vector. Okay, so the magnitudes in x direction, y direction, the rectangular components, x A B will be x A minus x B, y A B will be y A minus y B, z A B will be z A minus z B. So this is about O, and this how will write? MO vector equal to I vector, J vector, K vector. In place of x, you put x A by B, y A by B, z A by B. All these are coordinate distances, and this is fx, fy, fz. Okay, so this is about O, this is about B. Moment about B can be written this way, and moment about O can be written this way. So this is for any force in space. We can have the rectangular components, and we can use the determinant and find out the moment vector. Say, let us solve this problem. Okay, you have a rectangular slab, something is fixed by means of some clamping at A and B, okay, and also there is a wire, okay, C D. At D it is tied. Okay, so now what is asked is only this is the external force, the tension force that is acting, okay. About A, what is the moment? So moment about A of this force has to be found out. The magnitude of that tension force, I call it tension CD, okay. If I cut here and see, this is my TCB vector, okay, and this is the vector, and about this point we need to take moment. You see, the position vector is going to be this. This is R C, I write it here, R C about A. So this is the position vector. So this vector, this vector, this vector actually is in space, and this is the position vector, and this is the tension vector, and the moment direction would be something like this. This plane, it will be perpendicular to like this, about A. Then it will have X, Y and Z. Okay, X, Y, Z. So these components will be there. That is what we have to find. Okay, now we'll solve that. So as we know, just we learned about O, what is the determinant, about some other point. Here the O is here. Some other point, what is the determinant we have to use. So I'm going to use that. I vector, J vector, K vector, X, C, A, Y, C, A, Z, C, A, Fx, Fy, F, Z. Determinant. Now I have to just put all this inside and find out the determinant. If I use the determinant, we can find out the moment vector. Okay, so first we need to find out this vector. Okay, T CD vector is TCD magnitude and the lambda vector. What is this lambda vector? Lambda vector is CD vector by CD. What is CD vector? It is dxi vector plus d, I'll write it here, dxi vector plus dyj vector plus dz k vector. The x distance, y distance and z distance by what is CD? Dx square plus dy square plus dz square. We know the coordinate points. For CD, what is that? What are the coordinate points? So C coordinate point is with respect to this reference. If we take x distance is 300, y distance is 0, because O and C are in the same plane, and z distance is positive. This is 80, 240 plus 80. So 160, 240, 400. Right? And what is D? Coordinate D. X distance is 0, y distance is 240 positive, and z distance is 80. Okay, as we have already discussed, when you are finding CD vector, okay, your point of interest here, this is the point. C is the point where the force is acting. So C will become x1, y1, z1. This is x2, y2, z2. Okay, then x2 minus x1 is this, minus 300, y2 minus y1 plus 200 j vector, 80 minus 400 minus 320 k vector divided by under root 300 square plus 200 square plus 320 square. Okay, so now TCD vector is 200 into the lambda vector. Okay, so the final TCD vector is vector plus 96 j vector minus 128 k vector. This is the force vector. So what is this? This is fx, this is fy, and this is fz. We can substitute this. Now we need to find out x c minus xa. Okay, xc minus xa, yc minus ya, zc minus za. So xc minus xa, a is here, so this distance, so 300 minus 0 is 300, y in the same line, c and a are in the same line, so it is 0. Then zc is 80, 400 minus 320 equal to 80. Okay, so we have found out 300, 0 and 80. Now we have got the values, we have to find that. A vector is I vector, J vector, K vector. So I am substituting this in meters. 308 minus 120, 96 minus 128. Now we find out the determinant. So I 0 minus 96 into 0.08 I vector J minus J vector 0.3 into minus 128 minus 120 into 0.08 plus K vector into 0.3 into 96. So the final, if you simplify it, you get minus 7.68 I vector plus 28.8 J vector plus 28.8 K vector. So this is the answer. So this is the x component of moment, y component of moment, z component of moment, and it is the multiplication of the force and distance. So the unit is force, unit is Newton, the distance meter is, unit is meter, so the unit for moment is Newton meter. Okay, now can we draw this here about this point? Okay, so my x is negative, this is 7.68 I vector, 28 positive, 28.8 positive, and this is 28.8 positive. So x direction, y direction and z direction. Now we will discuss two dimension. That means the force is acting in the plane. Okay, that means in the same plane. If this is the force vector and see x, y, z, this is O, this is the position vector R. Okay, then we can have the x fy j vector. Okay. The magnitude of moment about O is, okay, if you take this force, we know already moment is force into perpendicular distance. So this force about O, the perpendicular distance is this. What is this distance? This is the x distance. Okay, so this is x. What is this distance? This is y distance. Okay, for this force, it is anti-clockwise. See, understand this carefully. It is in the plane. Obviously, the moment direction is in the z direction only. It's away from the board. This is the direction. So when I rotate this produces anti-clockwise moment, and the direction is this. Okay, so Fy positive into perpendicular distance is x. So we have to take this force also. It is producing a clockwise moment about O. It is producing a clockwise moment. It is going like this. It will rotate clockwise. So it is a clockwise moment, and my thumb is facing inside. So it is negative. Fx, the perpendicular distance is y. You need to understand this. Okay. If you have to take moment about some other point, then your x distances, if this is a, as we did for the three-dimensional case, it is xa minus xb, ya minus yb. Okay, that distance we have to take. In other words, you just see the point, okay, and look at the perpendicular distance, right? Now let us solve this problem. The question is, find moment about O. So we have to find moment about O of this force 600 Newton. Okay, so we know the definition of moment equal to force into perpendicular distance. Okay, so the force is known, and only the perpendicular distance we have to find. All the dimensions are given, we have to find out the perpendicular distance. How to find out the perpendicular distance? Okay, so you draw a line, an imaginary line, parallel to this force passing through O. Okay, I am drawing a parallel line. I hope with this parallel, right? I am drawing a parallel line. Now you can extend this anywhere in the line of action. Okay, this distance is the perpendicular distance. This distance is the perpendicular distance. I can draw through this O also. This is the perpendicular distance. Okay, all these distances are same, so this is the perpendicular distance. Okay, now what is this distance? How to find this? We have the inclination 40 degree. Okay, so I use this geometry to find out that. I am drawing a perpendicular line. So now this is perpendicular. Okay, this is perpendicular. Okay, and I also draw another line which is parallel to this. Now I got a triangle. So this is 40. When that is 40, this is also 40. Okay, so now this hypotenuse distance is 2 meter. Okay, so then this distance is, this opens like this. this distance. What is this? 2 sine 40. So this is 2 sine 40. So 2 sine 40. So 2, this distance is 2 sine 40. Fine. Okay, now this is 4 meter and this is 50 degree and this is going to be 40 degree. Okay, so this 4 is the hypotenuse and we need to find out this distance, which is nothing but 4 cos 40 degree. Understood? And this force is producing a clockwise moment about O. You see the arrow? It is rotating the body clockwise. So it is going inside. So conventionally we use negative. Force is 600 and the perpendicular distance is 4 cos 40 plus 2 sine 40, which is minus 600 into 4.35 something and minus 2610 Newton meter. 2609 point something or 2610. So this is the answer we have obtained. Now you see, finding out a perpendicular distance, how much we have to think and use the geometry to find out the perpendicular distance. That is very, very important. What is perpendicular distance? I am repeating. The perpendicular distance is the force, the line of action of the force and to the point about which we are to take the moment. Okay, for that draw an imaginary line which is passing through O and which is parallel to the force, and the distance between two parallel lines is the perpendicular distance. Okay, so we obtained this. Now, is there any other means to solve this problem? We'll think. Here comes the Varignon principle. See here. Is there any other means? As already we have discussed, we can resolve this into components. This is 600 sine 40 and this is 600 cos 40. Now we have resolved into components. We can forget this now. Now you see the perpendicular distance for this force is 2 meter. How to do it? Draw a line, imaginary line, which is passing through O, parallel to this force. Now these two forces are parallel and this is the perpendicular distance. So this perpendicular distance is 2 meter. Already it is given. For this is the line of action of the force and this is the parallel line. This is the perpendicular distance. The perpendicular distance is 4 meter. Okay. So now how to find out that? MO, again this is producing clockwise moment. So negative 600 sine 40 is the force and the perpendicular distance is 2 meter. Okay, and this force is also it is also producing a clockwise moment. Okay, so negative 600 cos 40 into the perpendicular distance is 4 meter. So when you calculate this, you will get 2610 Newton meter. Now we know the principle of transmissibility. The same line of action we can move the force anywhere. I can move this force here. This is 600 cos 40. This is 600 sine 40. Now, if you are moving here also, the effect will not change. Momentarily you forget about the point of application. Okay, so this will not produce a moment because this force is passing through O, which is not having perpendicular distance. So you can leave this. Only this force, a clockwise moment, so it will be sine 40, but the perpendicular distance we have to calculate again from the diagram. So that is tedious here, so we can avoid that, but we can solve that way also. By the same token, we can also put, now forget about all these forces now, we can put it here where this point meets. Here you will put 600 cos 40 and 600 sine 40. The 600 sine 40 force is passing through O. This will not produce moment. This will produce a clockwise moment. Again, it is going to be 600 cos 40 and into the perpendicular distance. What is the perpendicular distance? This is the perpendicular distance. Again, finding out perpendicular distance in this case is difficult. So, according to me, if you use the components and straight away you find the perpendicular distance which is given, you can find the moment about O. I hope you have understood. Try to solve more problems in order to understand the concept of moment in 2D as well as 3D. Thank you.